In this module, we will again talk about Gaussian distributions. If you're watching this module, I'm assuming that you have already seen the module 3.2, which was also on Gaussian distribution. If you have not, I would recommend first visiting 3.2 and then looking at this one. We first briefly summarize some of the key concepts of Gaussian distribution that we have also seen in module 3.2. So for a given random variable x, the Gaussian distribution, so this is a scalar random variable. The Gaussian distribution can be defined with this function. So the trend of the Gaussian distribution is so shown on the right. And for this function, the expectation is mu, the variance is sigma square, and we have also derived this mathematically and proved it in the previous modules. And here we show variations of mu and sigma square and show how the Gaussian distribution changes. So originally, if mu is equal to 0, all the distributions are centered symmetric and centered at 0. And with change value, for example, for mu equal to -2, the distribution shifts here. And the sigma square term, it controls the steepness of the distribution as well as the width. So for example, if we see for sigma square equal to 0.2, the distribution is very compact and it's very steep. And for sigma square equal to 1, it's relatively flat. And for example, for sigma square equal to 5, we see the distribution is very flat. So this is the distribution. These are some of examples of the Gaussian distribution. Note that this is for scalar random variables. And we have derived several properties of these Gaussian distributions. And we also perform maximum likelihood estimation of the model parameters mu and sigma square. We also perform maximum a posteriori estimation. And the same concepts also hold for vector random variables. So if you have random variables which are, for example, here d-dimensional, the distribution can be represented with this expression where d defines the dimensionality of the vector. And here's sigma's term is a d by d covariance matrix. Mu is a vector, d-dimensional vector for mean. And the expressions are very similar to how we work for scalar, but in just d dimensions. And when we perform maximum likelihood estimate, the mu turns out to be this expression, so average over the n values of x, and the variance can be represented with this expression. So this is for vectors, and for scalar, this term becomes a scalar, and this becomes sigma square equal to summation x n minus mu ml whole square. That's for the scalar terms. So this is the solution for the maximum likelihood estimate. And we also had checked whether the maximum likelihood solution gives us the true estimates or not. And for this, we also analyzed the biasness of the estimator, so biasness of the maximum likelihood estimate. And what we have shown in 3.2 is that the maximum likelihood estimate is unbiased for the estimation of mean for the Gaussian distribution, but for the estimation of variance, it is biased. And what we have also observed was that the estimated covariance is equal to n minus 1 over n times the true variance of the distribution. And for this, we then apply this correction of 1 over n minus 1, and this becomes the true variance of the system. So again, for the scalar, it becomes sigma square, and this is the covariance matrix for the vector random variables. So this is something we have seen in the previous module, and now we briefly discuss some additional properties of the Gaussian distribution. So the first one is conditioned Gaussian distributions. If we have two random variables xa and xb, and if we have a joint distribution represented by pxa xb, which is Gaussian, then the conditioned distribution, so the probability of, so the distribution defined by this xa over xb, or the distribution again defined by xb given xa, so p xb given xa, both these distributions are also going to be Gaussian. This is called the property of conditioned Gaussian distributions. Then the other one is marginal Gaussian distributions. If we have a joint distribution defined by pxa xb, then pxa can be, when marginalized with respect to the random variable xb, so the distribution, when the distribution is random marginalized with respect to xb, the output distribution is also Gaussian. And this property is defined by the marginal Gaussian distribution property. And we look at these two properties from this very simple example. So in this example, what we see is, on the x-axis we have random variable xa, on the y-axis we have random variable xb, and we have a distribution which is a joint distribution which is Gaussian. So this green one, this is the joint distribution which is Gaussian. First we look at the conditioned Gaussian distribution. So in this case, what we do is we take this line xb and we take the distribution of xa with respect to xb for a certain value of xb. So we take the distribution for xb is equal to 0.7, and if we run across this line, we obtain this. So we obtain the red curve. So what we see is the red curve is still Gaussian. So that is the property of conditioned Gaussian distribution. When our xa is conditioned over a certain value of xb, the conditioned distribution is still Gaussian. That's what we see here. Now we look at the marginalization property. So what we do now is we marginalize the disjoint distribution with respect to all possible values of xb. What that would imply is to just take the projection on this axis, to take the projection of all the frequencies of occurrence, the probabilities over this here, that would reflect something like this. So what we obtain is, when we take the summation over all possible values of xb, we obtain this distribution with respect to xa, and this distribution is still Gaussian. So that's the marginalized property. Next we discuss Bayesian inference for the Gaussian. We have a set of observations x. So we have defined by x, we have n different observations, and the likelihood function for this is defined used with this expression. So the product of the probabilities of observing each of these values of the random variable given mu. So, and this product can be expressed with this expression. And for performing the Bayesian inference, what we need is to also have a prior over the weights. So it is common to assume a Gaussian prior over the weights defined by mu naught and sigma naught square. And this serves as a conjugate distribution, and the product is also Gaussian. So this is our likelihood function, this is our prior, and when we take the product, the resultant posterior distribution is also Gaussian. And if we solve for the expression, the posterior distribution can be expressed with mu n and sigma n square, and it results into an expression of something like this form. So what we have is the mu n and 1 over sigma n square. We can denote with this. And since we have, so what we see here, at least what we see is now for the mu n is equal to, if we see this expression, it's a weighted summation for mu naught and mu ml. Here mu naught is the mean of the prior distribution, and mu ml is the mean that we obtain from the maximum likelihood estimate. So we, from the likelihood function, when we solve for that, this is the mu ml. So mu ml is this expression. If we put it in more simple terms, what we observe here is that the resultant posterior is a sort of compromise between the, we are talking with respect to the mean. So the resultant posterior mean is a compromise between the prior mean, so mu naught, and the maximum likelihood solution mu ml. And this is also illustrative from this picture. So in this picture, what we see is when we have no observation, so when n is equal to 0, the distribution purely relies, so we are talking about the mean again, the distribution purely relies on the prior. So that is it. So we have this distribution here, which is symmetric across 0. Now what we do now is, when we start adding samples, so when we have first one observation, when we have two observations, when we have n observations, each of these observations, so the observations that we obtain, for example, 1 observation, 2 observation, 10 observations, each of these observations are obtained from a Gaussian distribution with mean at 0.8 and variance of 0.1. So note that the prior had this is centered at 0. Okay. Now, when we are getting new observations, these observations have the mean at 0.8. So when we add one observation, we see that the mean has shifted here. When we add two observations, the mean shifts slightly more. When we add a lot of observations, so for example, when we add 10 observations, the mean has shifted from the prior to the mean of the observed data. So here. So that's what is also reflected from this expression. This expression is a balance between the prior mean and the mean obtained from the maximum likelihood estimate, and the maximum likelihood estimate has this term n. So when you have not observed much data, the Bayesian solution relies mostly on the prior. But as you keep on observing data, new samples, the solution slowly starts shifting toward the likelihood solution. Now, the next concept that we are going to talk about is the mixture of Gaussians. In simple words, mixture of Gaussians refers to just linear combinations of the basic Gaussian function. The Gaussian function has its own limitations. It has a very fixed defined shape, and it can only fit well on the data that has the similar simple shape. But that's not the reality always. Data can be distributed in more complex shapes than just Gaussian. And rather than trying to search for other distributions, it is very common to use mixture of Gaussians. And mixture of Gaussians, when you combine with suitable coefficients, they are shown to approximate very complex functions, even up to an arbitrary order of accuracy. And to understand the mixture of Gaussians, we see this example. So in this example, what we have is, this is a very popular old data set, the old faithful data set measurements. But for simple terms, let's put it like this. So on this 2D plot, what we have is a lot of green circles. These are observations. And then, we see that there are two chunks here. So we have some observations here and we have some observations here. And when we try to fit a single Gaussian over all of these, there is going to be a lot of error, because we see that the peak of the Gaussian is neither in this part, neither in this part. So it fits very badly. On the contrary, when we fit two different Gaussians here, we see that the peaks overlap with the high frequency zones in both these lobes. So this gives an intuition that combination of Gaussians could reduce the error to a significantly larger extent compared to fitting just one Gaussian. That is the motivation for using mixture of Gaussians. So the mixture of Gaussians, it is expressed as a linear combination of the Gaussians, and this pi k, this term, this is called the mixing coefficient. The overall summation of these pi k's is equal to 1. So this means that so this is the weighting term, so it's a scaling term, and the summation has to be 1. So this is an example of the complex distribution formed using the linear combination of Gaussians. So we have three Gaussian distributions here, 1, this blue one, 2, and this blue one is 3. And when we mix them using with a linear combination, the red curve that we obtain, that is the mixture of Gaussians. So we see that this is quite a complex distribution, and the complexity of the shape can be controlled with these mixture coefficients. This is another example to give you an intuition of the mixture of Gaussians. What we have here is, we have three different Gaussian distributions, the red one, the green, and the blue. And the combination of these three Gaussian distributions, the resultant probability density function has this shape in 2 dimensions. And here we show the surface plot. And if we want to define the probability distribution for the mixture of Gaussians, the log of the probability can be expressed in this form. It's just a simple extension of the original Gaussian distribution. Thank you.